So let's see here. Okay, so it says particle with some mass is moving along x-axis, and the question is actually giving me a time-dependent wave function. So, and this time dependence is wrapped into this portion here, this phase factor, and with this particular wave function, I guess it's meant to be a, I don't think it's an energy eigenstate. So, yeah, so I don't know how valid this is, but to some, so part of me questions if what the question is trying to do, set this E to be a constant, is something you can do. But at the same time, I want to say, okay, that's above my pay grade. I'm just going to go through the mechanics of the calculation because if the question gave me something that's not actually physically totally valid, that's on the question writers. It's not on me. I'll just work through it. So part A, it says, find the normalization constant A. And really all that comes down to is we want to impose this condition here. We want to say that when we integrate the absolute value squared of the wave function over all space, this represents probability density. And we want to say when we add up all the possibilities, that all the possible possibilities add up to 1 or 100%. So let me watch here. So my X, so this particular description of wave function, it's valid only up to X equals 0. For negative values of X, I'm just gonna say, I'm saying my wave function is 0. This particular expression only holds for positive values of X. So let me write this out. So what it's wanting us to calculate here, let me do this off on the side here. Integral of from negative infinity to infinity, absolute value of psi squared dx. I'm going to put in certain interpretations that need to be put in. One of them is, so because the function is piecewise defined from negative infinity to 0 and from 0 to positive infinity, this integral needs to be split into from negative infinity to 0 and 0 to infinity. And this portion of the definition says that this portion of integral is just going to be 0. So in the spirit of simplification, I'm simply going to write this integral from 0 to infinity. Because for one part, if I did the integral, it'll all vanish anyway. And this absolute value squared, what this is, psi complex conjugate times the function itself, dx. And this is going to simplify some of the expressions quite a bit. This is what I'm looking ahead to. I'm looking ahead to taking the complex conjugate of this wave function here. It actually has one part that only has real functions, and all the complex part is here. And this is looking like, e to the minus I phi, where all of phi is real. So when I do the complex conjugate, e to the plus I phi, and multiply it, they're just going to cancel out and give me 1. So this multiplication, it's going to end up being just this real part squared. So when I write this out, this expression for integral becomes a squared x squared times e to the, so when I do e to the minus alpha x squared, it'll become e to the minus 2 alpha x dx. Okay, I guess that this is the kind of question where you could do. I think the traditional way to do question like this is integration by parts. This is your U, this is your dV, and you might remember integration by parts. Now, this is what I'll tell you. You're welcome to do integration by parts. And what I am going to do is I'm going to use computer algebra system. So integrate. I think I'm just going to stick to this x squared into the minus, yeah. So x squared times exponential of -2 times alpha times x from x equals 0 to x equals positive infinity. Because it's one of those things where you're skilled to do integrals by hand. It's great to have. I'd love for you to have those great skills. And if you didn't, that's there are tools that can do the integral for you automatically. In terms of engineer and a physicist skill set, what is valued is not your ability to do this, which machines can do very easily. It's your ability to tell the machines what to calculate. That is what's valued here. So, so I'm just gonna use that, and let me actually take a screenshot of this so that I can not have this go away while I'm trying to copy it down. So I'm gonna do the part that that's fit for intelligent sentient being to do. So I'm gonna take care when I copy down the result. So I vectored out a squared. So I'm gonna write that down still, a squared. And the rest of the integral is what Mathematica did for me. And me looking at this, alpha is that I know. Oh yeah, that's positive. So or real part of alpha. Yeah, Mathematica does this which I guess is a good thing. It assumes quite a few quantities are more general than they are supposed to be. So it's fine. So I know this answer applies to our situation. So it's going to be a squared times 1/4 alpha to the third power. And the condition I'm applying here is that all of this should be equal to 1. And the remainder of the work works out to be to solve it for A. And when you solve it for A, you will get A is equal to square root of 4 alpha to the third power. And by convention, we take the solution where it's positive and real, and acknowledging that there are other solutions out there that technically fits that equation. But the convention that we use that simplifies certain things is that normalization constants, we pick it to be positive and real. That's a common convention that we follow. So yeah, that's A. It's a kind of so setting aside some of the concerns about if this is an actually possible wave function, the kind of the calculation you go through is quite mechanical, and getting through some of the more harder integration part, it isn't that hard. Okay, so it asks, find the probability that the particle can be found on this interval if L is equal to 1/alpha. So let me tell you what the equation that you should set up is. So this is what the wave function looks like. Looking at this and kind of squinting at it for a while, I think if I were to plot psi of x at time equals 0 as a function of x, then on the left hand side, in the negative side, it's gonna be 0, and then at x equals 0 or close to 0, it's actually going to shoot up to something close to infinity. because wait, no, actually it's gonna rise from zero. It's gonna rise from zero to, so as x increases, this portion is linearly increasing, this portion is exponentially decaying. So a product of those two is gonna look something like initial linear rise that's killed by exponential decay. So this is kind of the form of the wave function. And what we just calculated is, if you imagine taking this absolute value squared, which is kind of going to look similar to what I just sketched, when you calculate the area under this whole thing with the proper normalization constant, it should be 1. What the question is asking for is, let's say instead of going from 0 to infinity, you went only from 0 to some finite value. Then what is the area under the curve? That'll give you the probability of the finding the particle within this region. So the calculation you set up is surprisingly simple. It's actually the exact same calculation that we set up here with a very slight modification. So this probability to find, let me call this P. What that's gonna end up being is the integral of from 0 to L, or 1 over alpha, of the exact same expression. So it's going to be exactly this, a squared x squared e to the minus 2 alpha x dx. Oh, and yeah, and I think I can actually do the rest of the calculation on Wolfram alpha. Let me try that. So I'm gonna type in a version where a has already been factored out. In fact, I'm gonna put in the expression for a in terms of this normalization constant that we got. So it's gonna be integrate. So that thing squared. So 4 times alpha to the third power times the constant, it can be inside the integral, outside integral, doesn't matter, times x squared times exponential of minus 2 alpha times x from x equals 0 to x equals 1 over alpha. I think this is a definite integral that Wolfram alpha can just do. I think. Yeah, it gives you a numerical thing. It told me the answer, 0.32332. Let me just plug in the number and see, 0.323. 0.323. Yeah. So yeah, that's so the hard part here is knowing what integral to set up. Once you have that set up, then the rest of the calculation, I mean, if you insist on doing it by hand, then it is a lot of work working through integration by part. But if you are willing to delegate to the computer algebra system, then you get the answer quite quickly. So it's in part C and D where this setting up of there's an aspect of this where the question, the calculation that you're setting up gets a little bit esoteric. That this is the way we set up expectation value calculation. And in the lecture, I worked through this and gave motivation for why this particular calculation gives the expectation value. And I think for those of you who are looking at it and not quite having a good physical intuition for why this very weird looking thing is giving you the answer that we are looking, I think one thing that I would encourage you to look at when we get to it, I think next week, is this optional page. So I was thinking through if I should cover expectation value calculation in more detail. And when I was putting together next week's material, what I think will give you some kind of guidance to work through some of this abstract mathematical aspect of quantum mechanics is this activity that in the past semester we did this lab, and this semester we won't, but the instructions are here, and the set of calculations are set up here. This goes through more of the explanation of the linear algebra stuff. That's really the underlying foundation of some of the mathematical procedures we have. So I would encourage you to look through this next week as we are covering chapter 8 material. So and this kind of gives you the motivation for how expectation value, the procedure we use actually does give the quantity you expect to measure on average. So I'll have you look at that on your own time. It's kind of optional material. For today, I will set up the calculation. So setting up the calculation in terms of following the procedure, it's actually quite easy. There's a, I think I will mention this in other contexts. There's a saying in physics, shut up and calculate. Because in a lot of the contexts, the calculation itself is a lot easier than the physical meaning you assign to it. Doing this calculation, it's actually really easy. If you're just following this formula, then this is what you would say, all right. My expected position value is, okay, I'm gonna integrate from 0 to infinity. It's technically from negative infinity to infinity, but I'm lopping off the part that will go to 0 anyway. So the complex conjugate of psi, I think I might have it memorized. Let me try to write it down. The normalization constant times x times e to the minus alpha x times this part. I will just use the letter phi that I used before. It's technically a function of energy, time, and h bar and whatever, but it's the complex conjugate is going to be e to the plus I phi. I think that in the wave function you got, it had a minus there. Yeah, so it's going to be plus. And you sandwich in between the measurement operator x. The operator is just the x, multiplication by x. And the wave function itself is a times x times e to the minus alpha x times e to the minus I phi. And in this particular calculation, the operator, it doesn't really matter where you place it because it's a simple multiplication. It commutes, you can move it around. And so here it kind of works out simply. My complex conjugated part cancel each other out. So I basically have the psi absolute value squared. So I have a squared times, and then e to the, actually, yeah. Well, before I had x squared. Now I have x to the third power. So x to the third power times e to the minus 2 alpha x, because multiplying these two gives me that. E to the minus 2 alpha x dx. So that's the calculation you set up. Plug in a equals the square root of 4 alpha to the third power, and when you plug into when you plug it into the all from alpha. Actually, let me do that. I think this expression looks simple enough. I can just do that. It won't really take extra time. So it's gonna be integrate. Let me keep that normalization constant squared times here, instead of x squared, now it's x to the third power. And I think I'm keeping all this still. And instead of doing this from x equals 0 to this value, it's back to now being 0 to infinity. So before, with x squared, this would have been this would have been 1. And now with the x to the third power, I'm going to get some quantity that's not exactly 1. I think it's going to depend on alpha, because alpha gives me my length scale. and it'll be some numerical coefficient times, reciprocal of alpha, because alpha has a unit of inverse meter. So 3/2 alpha is my expected value. And that's the answer. I mean, I can do the question, but just to say out loud what my internal dialogue was, I have some doubts if this, I definitely have doubt if this particle is, so the question is rather vague on the whole setup. It's not actually telling you it's not telling you the potential function. So I think I can definitely tell you if the potential function were 0, then this is not an energy eigenstate solution. So trying to give it this definite energy eigenvalue would be wrong. But I think that's why the question is worded in this very specific way. And this E, it's a constant, so it doesn't really relate to anything. So in part D, that's the reason why it's asking for kinetic energy, not the total energy. Because within the question, we don't have enough information to explicitly calculate the total energy. Now, if the question were to ask you, then you would just give E as a given parameter. But it is actually not specifying the potential function. So you could almost imagine this as there is some potential well here that's forcing the solution to be of this shape. Never mind what that potential actually looks like. That's the kind of the fuzzy part you will make fit. Now, to answer this part, the calculation you set up is kind of, again, simple. You are just following this recipe, and I'm using this operator. So when you write it out, so this expectation value of kinetic energy, what it's gonna be is the expectation value of this operator, expectation value of momentum squared over 2m. And if I simplify it a little bit, 1/2m, that's a scalar multiplication, I can pull it out. And then it's gonna be expectation value of momentum squared. So writing this out explicitly in the integral form is gonna be the integral from minus infinity to infinity, but since my wave function vanishes where x is negative, it's gonna be from 0 to infinity. And I'm gonna have this wave function, a times x times e to the minus alpha x times e to the plus I phi. And then sandwiched in between, I'm going to have this operator, momentum squared operator. So that's gonna be h bar, this here is minus I h bar, the position derivative. So imagining applying this twice, I have minus I squared, so that's gonna give me -1. So -1 times h bar squared, I have 2 of those, and then 2 position derivatives, 2 derivatives with respect to position, times the wave function again. And this is where the order actually matters. So order matters in this sense. This operator here is acting on these functions, not anything to the left of it. So when you take these 2 derivatives, you end up, okay, so I don't think we are already over time, and I don't think I have time to actually work through this derivative here. So, you have product of x e to the minus alpha x. So you have to apply product rule here. So when you take the first derivative, derivative of the first term times just the second term plus the first term times the derivative of the second term, that's the first derivative. Take the resulting thing, you have to take the second. So let me actually just to do that part so that I can at least demonstrate the tedious calculation that you will have to go through. So the tedious calculation that there's no shortcut here other than using Wolfram alpha. But even then, I don't think it really simplifies it all that much. So the tedious calculation you have to do here is this double derivative of this functional form, x times e to the minus alpha x. So applying the first derivative, so that leaves just the one derivative outside. On the applying the first derivative, you have derivative of the first term, 1 times the derivative, just the second function, e to the minus alpha x, plus the derivative, the first function, x, times the derivative of the second function, which would be minus alpha times e to the minus alpha x. So here, what I'm applying here is the product rule, the derivative of product of two functions. You remember this from calculus 1? Is the derivative of the one function times the function itself plus the function of the other function times the derivative of the second function. So this formula is what I'm applying. That's what I got here, applying it once. And I have another derivative to apply. So let me do that. At least the first function kind of simplified, so I think it's fine. I can take the derivative there. I get minus alpha e to the minus alpha x. Here it still looks a little bit complicated, so let me work this out. It's minus alpha times derivative of the first function, x, so that's 1 times e to the minus alpha x plus the derivative of, or the first function, x, times the derivative of the second function, or minus alpha e to the minus alpha x. And you have to simplify this out, this expression algebraically. Let me do that and end this session there. One simplification I see is that e to the minus alpha x, I think that's in every term. So I can factor that out. So let me imagine factoring that out to the right-hand side. So what I'll have remaining that in the factored term is minus alpha. Minus alpha. And I have minus alpha times 1, so still minus alpha. And I have minus alpha times minus alpha, so that's going to be plus alpha squared. Yeah. And then I factored out e to the minus alpha x. So that's one piece of this calculation, and the most tedious piece, this part. And once you're done, plug it in, and minus h bar squared, and then you still have this function to multiply to. You'll get some algebraic expression that looks like that's gonna go as x squared times e to the minus alpha x, and do the integral as before. So